Hi, hello. This is Padmapriya, Assistant Professor of Statistics, Sri Sharda College for Women, Autonomous, Salem. Today, what we are going to see is the basic concepts of stochastic process. The first, what we are going to see is the definition of. Here, we see the definition of what is stochastic process. Stochastic process is a random process that refers to a series of events where each event through random occurrence has an inbuilt pattern. For example, in financial world, one uses the stochastic model to estimate the outcomes in uncertain situation concerning returns on investment, inflation rate, and market volatility. So stochastic process is nothing but a family of random variable with reference to the time. That at every time t in the set of t, a random number x of t is observed. So what is random variable? A random variable is a function from the sample space. So, for example, consider a random experiment, that is tossing a coin once. Here, the sample space will be the outcome, that is head and the tail. So, a random variable is a way of producing a random real number. Next here, this diagram shows that that is stochastic process is a series of events. That is event 1 with random variable 1 and event 2 with the random variable 2 and event 3 with the random variable 3. So stochastic process is nothing but the series of the events. So next thing is the basic components of stochastic process. There are two components of there are two important components of stochastic process. One is state space and another one is time parameter. What is state space? This state space can be further classified into two types. One is discrete state space and continuous state space. And the same, the time parameter also further divided into two types, that is discrete time parameter and the continuous time parameter. State space is nothing but the range of possible values of the random variable in a stochastic process is called the state space of the process. For example, if we are tossing a coin, what we are getting the outcome is the state space. For example, for tossing a coin, we'll get a random outcome of either head or tail. So the state space may be the outcome of the random experiment. This state space that can be further classified into discrete state space and the continuous state space. The second one is the time parameter. The time parameter in probability theory and statistics, a continuous time stochastic process or a continuous space-time stochastic process is a stochastic process for which the index variable takes a continuous set of values as contrasted with the discrete time process or continuous time process which the index variable takes only the distinct value. Here, the time parameter indexed can be either discrete time process or the continuous time process. If the time parameter is a discrete one with respect to the discrete time period, then it is a discrete time stochastic process. If the stochastic process is the continuous time with continuous time, then it will be a continuous time stochastic process. Now we go for the uh, types of stochastic process. So there are four types of stochastic process, that is discrete time, discrete state space stochastic process, that is the outcome of the random variable will be the discrete, and with reference to the time period will also be discrete. If both the components is discrete, then it is a discrete time, discrete state space stochastic process. And the second one is continuous time discrete state space. Here the time period is continuous and the state space is discrete. That is, outcome of the random variable will be the discrete. Then third one is continuous time, continuous state space stochastic process. Here the time period will be the continuous variable, continuous, and the outcome of the random variable, that is state space, it should also be a continuous one. Then it is a continuous state, continuous time period stochastic process. Fourth one is continuous time, sorry, discrete time and continuous state space. Here the time period will be discrete and the outcome of the random variable, that is the state space, will be the discrete. First, we'll see the discrete time continuous state space. Here, discrete time denotes a process sampled at a distinct point, often denoted by the n. That is, the time period will be discrete. That is 0, 1, 2, up to n. While continuous time denotes a process monitored constantly over a time, often denoted by t belongs to r. That is, a set of random variable, that is, set of real values. For example for example of discrete time continuous state space stochastic process. So, a queuing problem. This one is an example for discrete time, discrete state space stochastic process. Here, a bus taking a student back and forth between the dormitory complex and the student union office arrive at the student union several times during the day. The bus has the capacity to seat k person. If there are k or fewer waiting person when the bus arrives, it departs with the available number, that is k person. It takes the bus and reaches the union office and then again come to the student dormitory complex. If there are more than k waiting, the driver allows the first k person to board and the remaining person must wait for the next bus. The university administrator would like to know at each time period during the day how many students are left behind when the bus departs. That is, the number of students who are waiting for the bus in the bus stop is the outcome of the random variable, that is outcome of the random experiment. So the number of waiting at the bus stop is the discrete state space, and how many times the bus coming and going, that is the number of time the bus coming and departing, is the discrete time. So this example comprises of two component, that is state space, that is discrete, that is number of person waiting at the bus stop, and how many times the bus arrival and departs from the student dormitory and the student union office. So this is an example for discrete time discrete state space stochastic process. There are some different desirable characteristics of the system. The reduction in, we can also reduce the number by this forming this stochastic process. We can reduce the number of waiting at any time, minimizing the time a student has to wait for a ride, and minimum operational cost. So consider the number of students waiting at the time of arrival of a bus. When the time is counted by the number of times the bus arrived, then we again have it is nothing but a discrete time discrete state space stochastic process. Next, we see the discrete time, discrete state space. That is already what we see in the example is nothing but the example for discrete time, discrete state space, stochastic process. Here, the time will also be discrete and the state space will also be a discrete. For instance, the another one, the consumer preference are observed on a monthly basis. Then we have a discrete time, that is first month, second month, and third month. The discrete state base, that is on the first month, what is the preference of the consumer. So it may be a coffee, tea, or anything. So the both the state space and the time space both are the discrete one. A bus taking a student back and forth between the dormitory complex and the student union arrive at the student union several times during the day. So here also the number of time the bus taking the taking back and forth and the number of student is the discrete state space. So these two are the example for discrete time, discrete state space stochastic process. The next one is continuous time discrete state space, that is the time will be the continuous one and the state space will be a discrete one. In probability theory and practice, a continuous time stochastic process or a continuous space time stochastic process is a stochastic process for which the index variable takes a continuous set of values. That is, here the time will be a continuous set of variable and the state space will be a discrete state space. For example, consider the number of students waiting for a bus at any time of a day. So, in previous example, we consider only a during a daytime. But here, any time of a day. In this case, the parameter space is continuous and we speak about a continuous time. So, any time of a day, it may be morning, evening, or night. And the state space will be the number of students. So here the time period will be continuous and the state space will be a discrete one, that is number of students waiting for a bus. And the next one is consider the size of a population at a given time. So any given time the size of a population may be increasing over a time. It may be any in 2021 it will be a particular number and 2022 it will vary. So they didn't given any particular time, so it given any time. So we again have a continuous time and the state space will be the number of an individual, that is size of an population. So the population will be the finite and the time period is the continuous one. And the third one is continuous time and continuous state space. In probability theory and setting, again, a continuous time stochastic process may be constituted with the either discrete state space or the continuous state space. If the state space is continuous, then the stochastic process will be a continuous time and continuous state space stochastic process. For example, maximum temperature at a particular rate in a time interval. So time interval 0 to t. So the set of possible value of x of t, that means the outcome will be the continuous state space. The continuous random variable x of t, that x of t represents the temperature in a time interval of length t. So that is the temperature will be a continuous variable. It will vary from time to time. So morning the temperature will be morning the temperature will be 37 degree. At 12 o'clock it will even more than 37 degree. So it will vary. So the continuous in the state space is also continuous and the time period is it is in time interval of length t, that is interval of 1 hour, that is morning 10 o'clock, then 11 o'clock, then 12 o'clock, 1 o'clock, again 2 o'clock, 3 o'clock, 4 o'clock. So over a time interval period. So the time period also it is a continuous one. So this is an example for continuous time, continuous state space. Next, what we are going to see is a state transition probability matrix. Transition probability matrix is nothing but a matrix that is PJK, where the transition from the one state to another, that is PJK is nothing but the probability of the transition between state J and the K. So it is denoted as the transition probability matrix of the Markov chain. Markov chain is nothing but the discrete time, discrete state space stochastic process. A stochastic process which has the time space that is discrete and the state space time is discrete and the state space that is discrete. P is a non-negative square matrix. Square matrix nothing but it have the same number of rows and columns with the unit row sum that is the sum of the probability in each row will be equal to 1, and the probability values, that means pjk values, ranges between 0 to 1, and summation of pjk, that is a row of the row will be equal to row, the sum of the probabilities in a row is equal to 1 for every j. A non-negative square matrix P, that is transition probability matrix, with the unit row sum is equal to 1 is called the stochastic process. If we add the probabilities in the each rows, if that equals to 1, then that matrix is called the stochastic matrix. The state transition probability matrix. The state transition probability matrix of a Markov chain gives the probability of transitioning from one state to another state in a single time unit. It will be useful to extend this concept to a larger time interval. So first we can consider a transition matrix for any finite m cross m matrices. The matrix P is equal to Pjk, that is probabilities, is called the transition matrix or transition probability matrix of Markov chain. Is the unit if the sum of the probabilities in the unit will be equal to 1. So this matrix is called a transition matrix, state transition matrix. We often list the transition probabilities. That P11, P12 is nothing but the probabilities from the P11 is nothing but the probability of the event from the state 1, probability of transition from the state 1 to state 1, and second one P12 is nothing but the probability of the event from the state 1 to state 2, transition from the state 1 to state 2. So this matrix is called the state transition matrix or transition probability matrix, and usually shown by assuming the state, or then the state transition matrix is given by this one. This is because given that we are in this state, the next state must be one of the possible states. So if we are in the state I, the next possible state will be the I plus 1. Thus, we sum over all the possible values, that is all the possible probabilities in a row, we should get 1. That is the sum of the probabilities in a particular state is equal to 1. That is, the row of any state transition must be sum to. Thank you for patiently listening to the lecture and the basic concepts of stochastic process. Thanks you once again.